Last week, we talked a lot about energy relationships and, things like predation and competition and symbiosis. And then we got into energy pyramids, where only 10% of the energy goes from one trophic level to the one above it because of energy loss, right? Which is due to using that energy and converting it to heat and losing it to the atmosphere. The only energy that predators get from prey is the energy they use to build more of themselves. So that's the energy stuff. From there, we're going to move into chemicals, specifically the non-living chemicals that living things need. We're going to go with 3 of the more important ones. And since all living things need these chemicals have to cycle in and out of living things in certain ways. And we call those biogeochemical cycles. Not as scary as it sounds. Bio just means life, geo means earth, chemical means chemical. This is how chemicals cycle between living things and their environment, the earth. And our first biogeochemical cycle should be very familiar to you. Like, I think you even know a song about it. Which cycle am I talking about? The water. So, do you know the song, Abby? Okay, good. I'm not going to make you sing it. Nope. But you're all singing it in your head right now. I might make AJ sing it.
I actually don't know it.
You don't?
No.
Okay. I don't either. I just know there's a song.
If you guys learn.
So the water cycle. I think you know most of the key words here. There's really only one portion of it that you probably don't understand very well. We'll talk about that, and we'll talk about it much more later. But so we're going to draw each of these out, and in each case, we're going to start in the atmosphere. Leave yourself some space. When we start one of these, make sure you got at least half of the page left. So we start in the air. What form does water take in the air? What do we call water that's in the air? Clouds. What is that? What's the water that clouds are made of? What do we call it? Water vapor. And then from water vapor, we get condensation, where water vapor kind of coalesces. Why do I have an alarm at 7:45? I hope I'm not forgetting something important. Condensation, which is the water vapor kind of condensing into droplets of actual liquid water. And then precipitation is simply the water falling. What happens to the water once it falls to earth as rain? 2 things. What are the 2 paths it can take? Nothing? Oh boy. Brady?
Freeze.
It could freeze, sure. If it stays liquid, what's happening?
It pulls up.
It what? Pulls up. Then what? Maybe later. People do collect the water. It is rain. Where's the rain go? Where's the water go? There's basically 2 places that water can go. It can go into the ground. Absolutely. That's one. That's called seepage. And the other is that it can run downhill. And it tends to run downhill, joining up with larger and larger bodies of water until it reaches the ocean. Absolutely. So the second one that Tristan said is called runoff. Runoff is the term for that, for water flowing downhill along the surface of the earth into other bodies of water. And then, yes, you're absolutely right that eventually that water is going to find itself at the top of one of those bodies of water, exposed to that big nuclear engine in the sky that is the sun, and it's going to evaporate back into water vapor, which closes that half of the cycle. That's the part you're familiar with. Everybody knows that part, right? What most people aren't as familiar with is the below ground portion. That water can, instead of just running off, it can seep into the soil. And become what we call groundwater. And groundwater is different than most people think. It's certainly different than I used to think of it. When I learned about the water cycle as a kid, I always pictured underground rivers, like cool, like flowing underground rivers like you see in a cave system or whatever. It's not it at all. Groundwater is water that is very much entangled with the soil, like it's in the soil, like it's in the spaces between the soil. And it does flow, but it flows incredibly slowly, like inches per year. A good way to think of it that I was taught is like a slushy, like icy, whatever they get from a gas station. And the ice is the soil, and the syrup and water and whatever is the groundwater, and it's all kind of together like that. So that water then stays underground unless it's pulled up. One of the things that can pull it up is root uptake by plants. One of the other major things that can pull it up from the ground is humans, right? We dig wells and we pull groundwater up out of the soil, which is cool. Like your house can get all the water it needs from just a well that somebody dug. We'll talk about problems with this later, but the short story is that agriculture, especially in the West, pulls water out of the ground faster than it can recharge. And that's where the slushy analogy is really good, because it's like, you ever drink a slushy too fast? First of all, brain freeze, I know, but also, you get that kind of cone of dry ice that it's out of syrup. That's what happens to the ground, except it doesn't recharge nearly as fast as your slushy on a summer day. It takes like hundreds of years for groundwater to recharge. So the West is basically running out of groundwater. But that water that gets taken up by roots, there is a completion to that cycle as well, because all plants do what's called transpiration, where they evaporate water out of their leaves, out of these little holes in their leaves called stomata. And transpiration puts water back into the atmosphere. And that's the below ground portion that we're going to talk about, really. We'll talk about the groundwater overuse stuff in chapter 6. All right. That's the water cycle. Questions? Okay. From the very familiar, I think we're probably moving into pretty unfamiliar territory with the nitrogen cycle. Again, leave yourself some space. I've got nitrogen cycle in this slide written kind of in the middle of the cycle. So there's going to be 4 boxes basically on the compass points. So leave yourself room. Again, we will start it in the atmosphere. Is there nitrogen in the atmosphere? Is there a lot? Yeah? How do you know? What do you know about nitrogen? Don't know much about it? It turns out to be the, go ahead. It is a gas. Yeah. It's
nitrogen from the car. No, that's CO2.
That is CO2. We'll get there. That's the carbon cycle. Nitrogen turns out to already be the most abundant gas in our atmosphere. It's like 75%. And it's diatomic just like oxygen. N2 means two nitrogen atoms like to stick together. So you're breathing this stuff in high concentrations all day. What do you do with it? Your lungs do anything with nitrogen? Nothing. I mean, basically, there's enough air pressure that some of that nitrogen ends up dissolving your blood. But it doesn't do any good for you. Now, it becomes a problem. Anybody ever scuba dive before? So nitrogen is a problem for deep divers because when you dive deep enough below the surface of the ocean, the pressure increases. You know that, right? The atmospheric pressure increases, and what happens is it doesn't hurt or anything. It just causes more nitrogen to dissolve into your bloodstream. You don't feel it. It's fine. Not a big deal, except if you spend enough time down there and you come up too fast. Anybody knows what happens? What's it called? You don't implode. It's almost as bad. It's like, yeah.
Like oxygen buildup?
Not oxygen. We're talking about nitrogen, remember? And we put you under pressure so that a bunch more nitrogen dissolves in your bloodstream. But nitrogen's a gas. So if you come up too fast, what's that nitrogen going to do? Not just your brain.
It's a gas or expand.
So this is called the bends. It's a BENDS. It's a thing that divers get incredibly painful, can be fatal. What's happening is your blood suddenly starts to fizz. Your blood suddenly gets nitrogen bubbles in it because that nitrogen is coming out of solution and becoming a gas again. So imagine all of your blood bubbling at once. Not pleasant, right? So if you're lucky enough to have access to a decompression chamber where they put you back under pressure, but you're on the surface, and they lessen that pressure over a period of days, you're okay. Otherwise, it can kill you. But anyway, little side trip there. You actually do need nitrogen. Nitrogen is what makes up proteins and DNA and RNA. You gotta have it, but you can't use the nitrogen you get from the atmosphere. Who can? Anybody know what living things on this planet can grab that nitrogen from the air, pry it apart, and build things like proteins and DNA? Okay, then I have something to teach you today. Turns out it's bacteria. Only bacteria can do what's called nitrogen fixation. Splitting that N2 apart, it's very tightly held together. It's a triple bond. So only bacteria can do that. And what they do is they grab that nitrogen and make it into what's called nitrate, which is NO3, which can then be incorporated into proteins and DNA and RNA. There's only 4 boxes on this one, but they're big. So those bacteria we're talking about, most of them live in the soil, just kind of hanging out there in the soil. Some of them actually form partnerships with plants. There are a particular kind of plant called legumes that actually build little bumps on their roots just to house those bacteria. But regardless, plants are the next step. Bacteria get it from the atmosphere. Plants then take it and build proteins and DNA. And then everybody else gets them from plants. So bacteria are kind of the front door for these bacteria, for the nitrogen to get into the ecosystem. Bacteria are the front door. Plants take it from there. Of course, everything else depends on the plants. And then it turns out that bacteria are also the way that nitrogen gets out of living things. Because when living things die, it's bacteria that decompose them. And so separate, different bacteria called denitrifying bacteria are the ones that turn nitrates back into nitrogen gas and close the cycle. So again, tons of it in the atmosphere. None of us can do anything with it except bacteria. Once the bacteria get it, pry it apart, they make nitrates. They're in the soil or in the roots of plants. The plants take it from there. They make the DNA and the proteins they need. And then everybody else who feeds on plants, one way or another, gets it from them. When living things die, it's different bacteria called denitrifying bacteria that get the nitrogen out of the living things and back into the gas form. So nitrogen turns out to be pretty important as what we call a limiting nutrient. It's one of those things that tends to dictate how fast things can grow. Plants in particular. We'll talk more about that tomorrow, but today I want to get a little graphing under your belt. So once you're finished writing, go ahead and grab your device. Whoa. I'm sorry that you have to sit at those stupid desks. If I had my way, it would all be big black tables, but this year's weird. Go ahead and get into your Google Drive first and create a Google Sheet. It's the green icon with the white cross in it. Google Sheet. Create a new Google Sheet. I will demonstrate. Let's see. I just have to. Hit the plus button. Come on. So slow. Sheets is the green one. Create a new one. And then use another tab to go into your classroom. And I will drop the activity in that has the data for the graph you're going to make. So it's called cover crop graphing activity. Raise your hand if you've made a graph in Google Sheets before. Okay, it is not hard. You can totally do it. the graphing activity is going to look. There we go. It'll look like this. And the first thing you'll see is a description of an experiment and then a table of the data from that experiment. Like so. And so your job is going to be to make a graph out of that data. And it is perfectly acceptable to copy and paste that entire table into Google Sheets. You know how to copy and paste? Maybe you do it with the right click trick, but I will tell you that it's faster to do Control-C to copy and Control-V to paste, or whatever you want to do. And you're going to paste that into the sheet. Let's start there. Everybody do that together. Paste the table into the sheet. I'd also like you to name that sheet with your last name and then cover crop data. Your last name, cover crop data, paste that data in.
It's not doing the first one.
Huh?
It's not doing the first one. Try to fix the. So, like here. And I'll give it down.
Let's see if I can do it. For me. Oh, that doesn't matter. You just mean the first one's blank?
Yeah.
Not an issue at all. So if you've never graphed in Sheets before, it is literally as easy as highlighting your data. You know what I mean by highlighting, right? Turn it blue, like just click on top left and drag down to top right so they all are highlighted in blue with a box around them. And then insert. And then for some reason, spreadsheets don't like to call them graphs, they like to call them charts. And so you're going to say insert chart. And then you are going to change the type of chart. If it doesn't give you a bar graph, I think it likes to give you a line graph. Simply click on the menu thing that says line chart and switch it to column chart. That's what they call a bar graph. And you should be good to go. Once you've got that, click on the three, on the little menu of the chart itself and copy it. So there's three dots in the upper right of the chart itself. I want you to click on copy chart. And you're going to paste that chart right where it says paste chart here in the document that is your homework. So copy the chart, paste it into your homework, and now all you've got left is those questions. Good? All right, and this is directly related to what we just talked about those nitrogen fixing bacteria. So good luck. I'll let you use these last 7 minutes for working on that, and we're good.